Hi everybody, in this video we're going to talk about the models that we can use to help students understand addition and subtraction. So let's just do a little bit of vocabulary to start off. So when you're doing an addition problem, the name of the two parts that are being added together are addends. And when you add the two addends together, you end up with the sum. So the sum is basically the result of an addition problem. When you do subtraction, the larger amount is called the minuend, the smaller amount is called the subtrahend, and then when you do the minuend minus the subtrahend, that equals the difference. And technically, actually, it doesn't have to be larger or smaller because you could have a negative difference. But when you're first introducing addition and subtraction to your students, you won't be working with negative numbers. So to start off, the minuend will always be the bigger number and the subtrahend will be the smaller number. So addition and subtraction are both examples of binary operations. So a binary operation is basically one that has two inputs and you get one output as a result of whatever the operation does to those two inputs. So in the case of addition, you input two numbers and those numbers are combined together and you get the output of the sum. And there's all sorts of different binary operations. So we have addition and subtraction. Multiplication and division are also binary operations. And then you also have operations on sets, which we learned about a couple lessons ago, where you can find the union of two sets or the intersection of two sets, and that gives you a new set, or the Cartesian product of two sets, which also gives you a new set. So addition and subtraction are binary operations. And one of the things that we look at when we're looking at operations is we want to see if the operation is closed on a certain set of numbers. So say, for example, that we have the set of whole numbers. Well, if I choose any two whole numbers and add them together, so let's say I did like 17 plus 3. Well, that's going to equal another whole number. And regardless of what two whole numbers I choose, so I could choose like 0 plus 5, well, that still equals a whole number. And if I choose any pair of whole numbers and add them together, they will equal another whole number. And so what that means is that addition is closed on the whole numbers or on the set of whole numbers. And so that's what it means for an operation to be closed on a certain set of whole numbers. Now, there are some operations that are not closed on whole numbers, like, for example, subtraction. Because if I choose any two whole numbers and subtract them, like let's say 2 minus 6 or something like that, well, that equals -4, and the whole numbers don't include any negative numbers. And so that means that subtraction is not closed. Because if there's any group of numbers that if you put them into the operation and it doesn't give you another number in that same set, then that means that the operation is not closed on that set. So even though some subtraction problems will give you a whole number, like if I switch the order and I did 6 minus 2 equals 4, the fact that there are some whole numbers that when you subtract them, it doesn't equal a whole number means that subtraction is not closed. So why don't you try these next two and identify, is addition closed on the odd whole numbers and is addition closed on the even whole numbers? So pause this video and figure out what you think and then restart it to see what the correct answer is. Okay, so if we took any two odd whole numbers and added them together, our question is, will it equal an odd whole number? So let's just choose 2 to kind of experiment. So let's say I take the odd whole number 3 and I add this to the odd whole number 11. Well, when I add those two numbers together, I end up getting the number 14, which is an even whole number. And so this automatically tells me that addition is not closed on the odd whole numbers because I found two odd numbers that when I add them together, it equals something that is not an odd whole number. However, if I do even whole numbers, if I take any two even whole numbers and add them together, I should get another even whole number. Because like if I do, let's say like 6 plus 8, well, that equals 14. And it's impossible to come up with any group of two even whole numbers that when you add them together, it doesn't equal another even whole number. And so that means that addition is closed on the even whole numbers. And so this is the idea of closure. So what we're going to be working with is whole number addition and subtraction. And so one of the properties of whole number addition is that the sum of any two whole numbers will be a whole number because the operation of addition is closed on the set of whole numbers. There's also three other properties of whole number addition, and I'm going to go through these after we talk about some different models for addition so that you can see why these properties are true. So the first model for addition that you can use to help your students visualize addition is the set model. So the formal definition of this is if you let A and B be disjoint sets, then the number of items in the set A plus the number of items in set B will equal the number of items in the set A union B. So an example of this would be if I have set A be the set of these 2 toys and set B be the set of these 5 toys, well, when I union those 2 sets together, I get this new set, which is A union B. And if I count the number of items in each set, the number of items in set A is going to equal 2, the number of items in set B is going to equal 5, and the number of items in A union B equals 7. And so this is how we define the addition problem 2 plus 5 equals 7. And in this definition, it's really, really important that A and B are disjoint sets. Because if A and B were not disjoint sets, then addition would not be defined correctly. For example, if we have set A be the set that contains A, B, C, D, E, F, G, well, the number of items in set A is 7. If I have set B be the set containing A, E, I, O, U, well, the number of items in set B is 5. And if I do A union B, that's going to be all of the elements that are in A or B. So I'll have A, B, C, D, E, F, and G because those are all elements in A. But then I'll also need to have I and O and U because those are the elements in B that I hadn't listed yet. And if we count the number of elements in the set A union B, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But 7 plus 5 does not equal 10. And the reason that this did not create a true statement is because in this example, A and B were not disjoint. Because disjoint means that the intersection of the 2 sets is empty, but the intersection of these 2 sets would have an A and an E because both of the sets have an A and an E in it. And so if you're using the set model, you have to make sure that your 2 sets are disjoint from each other in order for this definition to make sense. So this is the first model that you can use. The set model basically says you have a group of things, another group of things, and when you combine them together, the number of things when they're combined together is the answer to the addition problem. And you can also do a measurement model for addition. So if I wanted to use a measurement model for addition, I would start at the number 4. So I'd go from 0 over to 4. And then I would add on 3 more from here. So I'd go 1, 2, 3 units ahead on the number line. And this shows that 4 plus 3 equals 7. So depending on the problems that you're solving with your students, you may want to use a set model where you use different objects and then you combine groups of objects together. Or you may want to use a number line model where you start at whatever number comes first and then you add on to that. And this is a helpful way of visualizing the idea of counting on. So now that we have these two models, let's go back and look at the properties. So the commutative property says that if you have two whole numbers, a and b, then a plus b is going to equal b plus a. And I can demonstrate this with a set model. So let's say I wanted to use a set model to model the problem 2 plus 3, and I'm trying to show that this equals 3 plus 2. Well, if I was to draw a picture of this, 2 plus 3 would basically be like 2 items and 3 items in a group, and then you would combine them together and you would have a total of 5 items. And if I draw a similar type of picture for the right-hand side where I have 3 plus 2, well, that's going to be a group with 3 things in it and a group with 2 things. And if I combine those together, I'm going to have 5 things. And so this is a really easy way to show that the order of addition doesn't matter. Or in other words, addition is commutative, where you can switch the order of the addition and it won't end up impacting your result. You can also use a set model to show the associative property. So the associative property says that if you add two numbers together and then add a third number, that's the same thing as adding the first number to the result of the second and third numbers added together. So let's say, for example, that this was 2 plus 3 plus 4 equals 2 plus 3 plus 4, where I need to do the stuff in parentheses first. So if I were to visualize this, 2 plus 3 is going to look like a group with 2 things and 3 things in it, combined together, which gives me a group of 5 things. And then that is going to be combined together with a group of 4 things. So these two are going to be combined together, and that gives me a total of 9 items altogether. And so that would be what the left-hand side of the equation could be visualized as. And if we have a group of 2 things that's being combined together with the result of 3 things and 4 things being added together, well, if I add the 3 and the 4 together and combine those groups, I'm going to have a group of 7 things. So there's 7. And then if I combine those two together, 2 plus 7 is going to give me a result of 9 things. And because those two results are the same, this shows why the associative property works, where it doesn't matter which parts you add together first. Because if they're all being added together, you can do it in any order and you'll still get the same result. And then the last property says that for any whole number a plus 0 equals a, which equals 0 plus a. So we could model this one on a number line. So let's say in this case, maybe the a is the number 5. So I'm trying to show that 5 plus 0 equals 5, which equals 0 plus 5. So on a number line, here's 0, here's 1, 2, 3, 4, 5, 6, 7, etc. So if I wanted to model this, 5 plus 0, I would basically start at the number 5, and then I would go forward 0 units, which means I'm just going to stay at 5. If I wanted to graph the number 5 for this part, well, that's just the number 5. So again, I end up in that same spot. And if I wanted to graph 0 plus 5, I would start at 0 and then go forward 1, 2, 3, 4, 5 units. And again, I end up in that same spot on the number line. And so this is a visual way to see that whether I take a number and add 0 to it, or if I do 0 and add that number to it, both of those results will equal whatever the number was. And the reason that these properties are important is because they give us thinking strategies that can help your students memorize their addition facts. And it will also help them think about addition in a way where they're not just memorizing facts, but they're actually thinking through what it actually means to add numbers together. So the first property, the commutative property, is really, really helpful because it basically cuts down the number of facts that we need to memorize almost in half. So this table here shows all of the different addition facts that your students need to memorize. And if you notice, if I look at, say, like this box right here, which is communicating that 4 plus 1 equals 5, because 4 is the row, 1 is the column, and 5 is the number that's in the intersection of that row and column. This answer is the exact same answer as this one right here. Sorry, you can't see that very well because it's red on red. But that one is showing that 1 plus 4 equals 5. And those two addition facts are almost exactly the same. The only difference is that the 4 and the 1 have switched spots. And the commutative property says that if you switch the order of addition, you still get the same result. And so that basically means that you only need to memorize one of them. You only need to memorize either that 4 plus 1 equals 5 or that 1 plus 4 equals 5, because once you have that memorized, then you can switch the order and you've got that fact memorized as well. And so basically, this commutative property cuts out all of these addition facts because all of those addition facts have a similar addition fact on the other half of the table that equals the same thing, and the commutative property allows you to switch the order on those. And so the commutative property alone cuts down your memorization in half. Then the next property, the identity property, says that any number plus 0 equals that number. Well, that allows you to memorize all of these addition facts, because if you have 3 plus 0 or 6 plus 0, you're just going to get that same number. And so the identity property allows you to memorize all of those facts. Then you can use a counting on strategy to memorize your 1s and 2s. So for example, if I have 5 plus 1, well, I can just say, well, 1 more than 5 is 6, and so 5 plus 1 is 6. Or if you are doing 7 plus 2, well, if you start at 7 and you go 2 more than 7, that would bring you to 9. And you could visualize this with a number line model using the measurement model I showed you guys earlier to help students be able to visualize those. And so by counting on by 1s and 2s, you basically can memorize all of this part of the addition table. Then the next strategy that can be helpful is to memorize the things that combine to 10. So obviously 5 plus 5 equals 10 because we have 5 fingers on both hands. But you can also do 4 plus 6 and 3 plus 7 and 2 plus 8 and 1 plus 9. And those combinations to 10 can give your students a really good like baseline calculation that will help when we use the associative property. So before I do the associative property though, let's finish up the doubles. So the doubles are basically memorizing what two numbers that are the same add together to be. So like 2 plus 2 is 4, 3 plus 3 is 6, 4 plus 4 is 8, 5 plus 5 is 10, and so on and so forth. And if your students have the doubles and the tens memorized, then this can make the rest of the addition table really easy to figure out using the associative property. So the associative property, so the way that you can use the associative property to memorize some of the addition facts is, let's say you had something like 8 plus 6. Well, the associative property says that it doesn't matter which things you add together first if you have 3 numbers that you're adding together. And so if you think about the number 6 as being 2 plus 4, then you can do 8 plus 2 plus 4 and add the 8 and the 2 together and then add the 4 on. And the reason that this is helpful is because 8 plus 2 is one of the things that add to 10. And 10 plus 4 is really easy, that's just 14. And so this is an easier way of thinking about it than having to count on and go like, oh, well, 8 to 9 to 10 to 11 and like counting on 6 numbers to get up to 14. It's easier to say, well, how much do I need to count on to get up to 10? And then how much more do I have after that? And you could do something similar, like if you had, let's say like 8 plus 9. Well, you might have your doubles memorized, and so you could think about this as 8 plus 8 plus 1, and 8 plus 8 is 16, so if you add one more to that, that would be 17. And so you could think about it that way. Or you could also think about this one as 7 plus 1 plus 9, which also gives you 17 because 1 plus 9 equals 10. So there's lots of different ways you can think about the associative property, but the associative property makes all of the remaining addition facts easier to memorize, assuming that you have your baseline facts of your combinations to 10 and your doubles. And you can also use these thinking strategies when you're adding bigger numbers. Like, for example, if you have 42 plus 18, you could think about this as 40 plus 2 plus 10 plus 8. And then you could use the associative property to change what you add together first. So you could change it so that you add the 2 and the 10 together like this. And then you could use the commutative property to switch the order and think about this as 40 plus 10 plus 2 plus 8. And then you could change the parentheses or what you're adding together first. And this way of thinking about it would be much easier to add these together. Now, obviously, you're not going to actually write all of these steps out usually. Like you might go directly from this step down to this one. But it's the commutative and associative properties that allow you to do that. And so once you're thinking about it like this, then you can say, well, 2 plus 8 is 10. And then if you add that to the 50 from 40 plus 10, 50 plus 10 will give you the number 60. And so you can teach your students these thinking strategies so that they can do addition facts like this in their head. And you can also do it when you're adding together numbers in other bases. So let's say, for example, you were taking 5 base 7 and you wanted to add 4 base 7. Well, if I wanted to make this easier, I could say, well, I know that my next place value is the 7's place value. So maybe I could think about this as 5 base 7 plus 2 base 7 plus another 2 base 7, because the 5 base 7 plus 2 base 7 will give me a 1 in my next place value. And so basically I split this 2 base 7 up into 2 2's, and then I can say, well, 5 plus 2 base 7 is going to be 1 0 base 7, because I have a 1 in my 7's column and a 0 in my 1's column. And then I would add this to 2 base 7, and 1 0 plus 2 is going to give me the number 1 2 base 7. And I'm reading this number as 1 2 base 7 so that we don't mix it up with the number 12 in our base 10 number system. Because 1 2 base 7 is equal to the number 9 in base 10. So those are the different thinking strategies for addition. So let's move on and talk about subtraction. So there's several different ways that you can think about subtraction and several different ways you can model subtraction for your students. So the first model is the set model. So if we have A and B, where B is a subset of A, meaning that everything that's in B is also in A, then the way that we define subtraction is we say that the number of items in set A minus the number of items in set B equals the number of items in the new set A without B. So remember that the set A without B is basically all of the elements that are in A that are not in B. So the set A without B would look just like set A, except it wouldn't include these two. And so if we look at this and we count out how many items are in each set, well, in the set A, there's 1, 2, 3, 4, 5, 6, 7 items. And then the number of items in set B is 2, because you have 2 items there. And then the number of items in the set A without B is 5, because you have these 5 items that are in A but not in B. And so you can see that this model describes how subtraction works, because the number of items in set A minus the number of items in set B equals the number of items in the set A when you take out the items in set B. And so this idea introduces subtraction as a takeaway type of a problem. And when you're teaching it to students, you can either teach it with a set model or with a measurement model. So a set model might look kind of like this, where you say, okay, here's our original group of things, and you might have like marbles or chips or blocks or whatever it is you're using. So let's say that I have like 7 of those. So in a set model, you start off with a certain amount, and then you take away or get rid of a certain amount. So in this case, I could model the problem 7 minus 3, and I look at how many are left, and there would be 4 left. And so that would be the set model. You can also use a measurement model. So in a measurement model, if I wanted to model 7 minus 3 equals 4, the way I would do this is I would start off at the number 7, which gets me to here. And then if I'm taking away 3, then I'm going to go backwards 3 units. So I go back 1, 2, 3, and that puts me at the number 4. And so that is the measurement model for takeaway subtraction. Another way that you can model subtraction is by using fact families and teaching your students about fact families. So a fact family is basically where you have 4 different math facts that are all related to the same numbers, and they illustrate the inverse relationship between addition and subtraction, as well as the commutative property of addition. So for example, if you have 1 plus 4 equals 5, the commutative property says that 4 plus 1 also equals 5. And the inverse relationship between subtraction and addition, which basically says that addition and subtraction undo each other, says that if I have 4 and I add 1 to get 5, well, if I take 5 and I subtract 1, then that will get me back to 4. So 5 minus 1 equals 4. And then similarly, 5 minus 4 also equals 1 because that undoes this addition fact. And this idea of fact families can help introduce subtraction as the inverse of addition. So another model that you can use to help your students understand subtraction is the missing addend model. So the missing addend basically rewrites a subtraction problem as an addition problem where part of it's missing. So for example, if you were trying to find out what 3 minus 1 is, the missing addend model would say that you rewrite this as an addition problem where you have 1 plus question mark equals 3. And then you use the set model or the measurement model for addition to help you find that missing number. So in the set model, you would say, okay, well, I have a group with 1 thing in it, and then I have a group with an unknown number of things in it. And if I combine these 2 together, I need to have a group that has 3 things in it. And you ask, well, what has to be in this group in order for the combination to equal 3? In the measurement model, you do something similar and you say, okay, well, if I have 1, then how much further do I have to go in order to get to 3? So I go 1 unit and then I ask, how much further do I need to go to get to the number 3? And on the number line, you can see, you just count, well, 1, 2 units gets me to the number 3. And so that tells me that 1 plus 2 equals 3. And so the answer to this problem would be the number 2. And then the last model for subtraction is actually the reason that we call the result of a subtraction problem the difference. Because the last model is to think about subtraction as comparison. So if we have a problem like, let's say, 5 minus 2, the way that you think about it in a comparison model is that you're comparing the number 5 to the number 2. And you can do this with a set model. So you could have a set with 5 items in it, and then you could have a set with 2 items in it. And if you compare these and make a one-to-one correspondence between these items, the difference between these 2 sets is 3 items. And so 5 minus 2 equals 3. You can also do this with a measurement model where you make a bar for the number 5, and then you make a bar for the number 2. And the difference between these 2 bars is 3 because there's 1, 2, 3 units between the numbers 5 and 2 on the number line. And so that's what a comparison model for subtraction would look like. So to summarize, addition has two different types of visual models. You can do a set model where you have two sets and combine them together. You can have a measurement model where you start at a number and then count forward however much you're adding to that number. And when your students are memorizing their addition facts, they can use the commutative, associative, and identity properties to help them memorize their addition facts. And then with subtraction, there's 6 different visual models you can use. You can use the takeaway models, either with sets or with number lines, where you start off with a certain amount and then you take away, or if you're doing a number line, you go backwards on the number line a certain amount. Then you have the missing addend visual model, where you think about the subtraction problem as an addition problem where part of it's missing, and then you look for the missing part. Or you can use the comparison model where you compare two numbers, whether it's with sets or on a number line, to see what the difference between the two numbers is. So that's everything for our lesson on addition and subtraction. On your homework, you guys are going to be exploring to see if there are any properties of subtraction that are similar to the properties for addition. So I hope you guys enjoy your assignment, and if you have any questions, let me know.